Alright, welcome to another one. This one is a bit different. I've been waiting to do this one for a while. I've had a lot of interest in this over the years when I just kind of mentioned it here and there. This is a truly optical processor with a sonic processing core. It's a piezophotonic gel compression core that uses light converted into sound, and the sound is converted into pressure waves, and the pressure waves through the piezophotonic gel emit pulses of light. Now those pulses of light are then again collected by micro-lens arrays, and those pulses of light are then, they exit the core. So it's pretty simple. You get light in, you get light out. And the complex bits in between are taken care of by pressure waves inside the dense photonic gel. As you know, sound waves can cancel each other out, they can reinforce each other, but you know, overall the waveforms that you're dealing with, you're dealing with actual waveforms. And since you're dealing with something that it's a little bit slower, you have to deal with basically a little bit more parallel than probably your single-threaded type of applications. This would be a massively parallel microarray. Without any further ado, let's go ahead and look at what I have on the board behind me. This is Optisonics sonic processor. Basically, you get optical in to these Q-trap cores, or Q-trap emitters. And the Q-trap emitters are made of alternating p-n junctions, which produce a sonic output. Now, of course, the p-n junctions create a standing wave. As the light pulse comes in, it converts the optical into mechanical, and the optical, as it propagates through the wave, or as the wave propagates through the material, this would be basically a CVD, carbon vapor deposition, little emitter with a blasted out little pit here. That's your Q-trap. So your full amount of your pulse coming in is used up, and you create a reinforced sonic output out. Now, these Q-trap sonic emitters are set up in an array format, top and bottom in this particular case, and there's you know, left by right, however many you can put around that. I haven't done the actual calculations because I haven't made any of these yet, but this is all concept. And the main thing is we can use sound to create the calculations, the complex, massively parallel, evolving equations. You can create an evolving equation on multiple levels inside this thing. You can actually have multiple equations running at once. So this can be an active simulation inside there that's going to produce optical pulsed outputs. And you're gonna get your answers. So your sound compresses the piezophotonic gel liquid, and then you get answers essentially from the peaks. Wherever the peak goes above a certain level, you get a flash of light. And that light actually, from what I could see, you could do this, if it's nitrogen, you could get any color of the rainbow. But specifically, let's just go ahead and deal with one light pulse out. Most likely, it's going to be infrared. Most likely. The most common way to do this, I think, in my mind, would be to use sonic in and infrared that would be able to penetrate the piezophotonic gel without loss. So you'd have a specific infrared out, and of course the infrared would be light pulses going out. So this is a very, very complex set of things you can do with this. This is when I see this in my mind, it's so complex, and we can create real answers to real world problems in real time at the speed of light. Literally, I mean, this is a slowdown, but at the same time, you're using multiple high-speed optical inputs to create this waveform core, and the waveform core then releases pulses of light in response to pressure waves. So these calculated pressure waves, the compression waves themselves, activate the light-emitting gel, and each light emission wavefront can calculate massively parallel evolving equations from a phased hypersonic acoustic array. For any of you who might or might not be familiar with phased hypersonic acoustic arrays, what those are is it's kind of like 3D sound. You can make the sound come from anywhere in a room. And that's essentially what these things are going to do. They're going to make it so I can literally put a compression in any shape, in any amplitude and modulitude, up to the maximum of the p-n junction sonic emitter inside here. And I can cool these to if I wanted to, I could, for example, if I wanted to go into the terahertz range, not that the gel could take it, but let's say it could. I could cool these off, and instead of using a p-n junction situation like this, I could use like a crystal. And the crystal I could strike with blue lasers, and of course I could get, I think it's 1.3 terahertz is the current record for the blue laser to sonic emission. So, it's pretty simple. It's going to be a short video. I don't want to spend a lot of time on this because I've got a lot of things to do. I promised my son I would do a video for all my inventions that I'm too poor to make. So those of you out there that want to build one of these things and change the world for the better, of course, go ahead and tell me about it. Post some videos, give me some links or something. Let me see your work. You know, you want to work out all the calculations and stuff. Great. This is going to change the world. This is definitely going to change the world. This type of technology, you know, it uses sound to calculate outputs from dense wave propagation through a photonic gel. This emits bursts or answers that can be decoded further with logical decode combination software hardware. Combination of both incoming waves induce photonic emissions in pattern sequences. And like I said, you can use the phased hypersonic acoustic array. This would be basically you'd use regular computer processors to run this one, to run the array, the input array. So it's going to be a two-step process. We're going to use the slower silicon processors, the single channel, or what are they up to now, like, you know, 200, 300 channels or whatever. This one processes on millions of wavefronts, you know, matching wavefronts. There's so many. It's like you can reinforce it, you can tear it down, you can create. This is going to be, I want to say, billions of times faster. Because, I mean, fine. Let's see. Because you're calculating out, it's you can have multiple stacked shells, you can have an evolving single equation, and the cool part, I suppose, would be that there's just so much complexity. I don't even think we're going to be able to garner or look at the absolute complexity of what's going on inside here. And that's why I want to use like an infrared out, so we can have all those internal layers, all these layers inside the highly compressed photonic gel core, make it out to the CCD array. So this is just a prototype kind of like design, just concept out there for you guys out there in YouTube land. You scientists, you geniuses, you leaders of people and corporations. Let's look at maybe building one of these, because I think it's definitely the next step. We have to use our best processors and our best software and our best software engineers to be able to even make one of these work. So. And once these work, then of course you've got another step of processing that's so much better. I just, you know, you're using nature, you're using nature's waves to do your processing for you. You could make a real planet Earth, like simulation, little tiny one, like with all the clouds and everything else. You could literally simulate a planet inside this thing. That's how complex I can see this becoming. And now, admittedly, it might take up a room, but most big computers, first computers, do when you're talking about a major simulation like that. But you can literally have an active photonic simulation of the planet Earth, or any type of thing like that. You know, that levels of complexity. You know, the calculus there is massive. You just all of these branched patterned equations are available with this type of processor. Anyway, so that's the Optisonic sonic processor. It is the next generation of thinking to create a bridge between the silicon and electron-based processors and computers that you're all used to, and go into the next level, or you know, like for finite analysis and things like that. This is going to change all of that. I mean, you know, a simulated world, all that kind of thing, you're going to be able to really simulate it. It's going to be so much better than, I mean, you're going to use physical, piezo, photonic, optical simulation. I can't wait to see what you can create with this. And this is just the first of many that I can't afford to make myself, and you know, I don't know if I have the patience to make this stuff. I mean, I'm sure that there's a lot of you out there that can. Okay, well, we had a package at the door and I had to go get that. But let's go ahead and finish this up real quick. So the object of this is to create something that is self-powering, it uses the optical in. So that's one of the problems with optical processors. And this is one of the things when I was younger, when I was a young warthog, I designed a optical timing loop. It's basically just a optical loop that goes around and around and around, but it consumed enormous amounts of power. And that's one of the problems, is trying to get an optical array like this to function properly. It takes enormous amounts of power. And when you're talking about something that's really, really small, you put tons of power in there and it tends to melt down. So this one's nice because it takes the optical in, which provides all the power that it needs to create the pulse in a wavelength and a modulitude and an amplitude that is high enough to activate the piezophotonic gel in various steps. So the real step, I think, is going to be the piezophotonic gel. You have to find a piezophotonic gel that will emit a infrared pulse, a light pulse. And it doesn't have to be a laser pulse. It just has to be a light pulse of varying amplitude and modulitude. And now, admittedly, it could be a multiple compound. You could have 2 or 3 different compounds. Now, I could go through, I guess, and figure out what those are, but I think you want to. I think you want to own this. You do. And this is what life's all about. I give you some ideas. You run with it. So run with that and figure out what it takes to create piezophotonic gel that can produce multiple wavelengths of light when compressed. There's probably a whole bunch of them. And it's going to be a compound. Anyways. And that will give you the power. Use the optical in to create the sound waves, which activate the piezophotonic gel, which emit the light pulses, and the light pulses go out, and those are received. And so this is kind of like a bridge, but also it's a true processor. You're using specific waveforms. You get cancellations, you get compressions, you get compounding, you get all of the math that is usually done via, electron pulses, I mean, those are admittedly speed of light, but this is massively parallel. Massively parallel. So this looks like a sphere, right? Well, let's go ahead and extend this out just a little bit. Oh, look, it's a cylinder now. Now, instead of having 12 of these little compression points, you have as many as you want. So you can literally make these things as big as you want, so they're optical processing sticks, which is really cool. But you probably start out with like little ball or a little cylinder. And that'll probably be the easiest way to put one of these things together. Anyways, I hope you enjoyed the video. Matter of fact, I know you enjoyed the video because this is next generation technology that you would have to have studied all these Engineering Digest magazines. You have to study all these different types of science and photonics. Photonics was my thing. And all these things to really understand how to kind of create this thing. It's almost like, how do we put this thing together? Well, that's how pretty much I think you should put it together. Anyways, thanks for watching, and I hope you liked the video. And this is going to be the first in a series of inventions that I'm just going to kind of give y'all, because what am I going to do? I don't have the facilities to make one of these yet. And these are world-changing. They will improve the AI presence here on Earth. They'll help make smarter computers, faster computers. You could have your watch that talks to you in the future. I mean, you could have a simulation. The simulations that you can run with this thing are incredible. At least I think they will be. So, once again, make sure you thumb me a like and subscribe if you haven't subscribed already. I love seeing all the subscribers. Every time the number goes up, I was actually surprised. I went in there, I'm like, I didn't know I even had any subscribers on this channel. I'm like, huh, there's actually people. Alright, well, I might as well go ahead and use this one to send these out there. Anyways, I'm Zio, and you're watching Zio205IQ. That's me, and we'll see you again real soon. Bye.